welcome to Introduction to Campus Network Design and Multilayer Architectures. This is session BRK ENS 1500. In case you missed the room, this is the reminder. My name is Jakub Matela. I'm a senior solutions engineer, currently part of the America sales. I'm focusing on a strategic financial sector. And previously I was focusing, well, for the past 9.5 years, my focus was fully campus switching and related architectures like software-defined access. Right now I shifted my focus to the data center switching, but campus switching is still close to my heart. That's why we'll be talking about that today. I strongly encourage you, if you haven't done so already, to join the dedicated room through your Cisco Live app. You'll find this button, Join WebEx Conversation, and this is where I'll be able to handle more specific questions. If you have questions, you see that this room is quite long. If you have questions related that could benefit broader audience present today with us, then feel free to ask that question. Otherwise, if it's more your design, corner case specific, let's have that conversation of the WebEx, then it's going to be easier for me to refer some materials, and everyone will be able to benefit that answer too later on. If you didn't know, this session is part of two series-long breakout session, which are covering campus architecture from the very basic foundations all the way to more advanced topics. So we will be covering across these two 90-minute long sessions, we'll be covering the 6 main topics, which is the fundamentals, principles of building a network through the foundational services, or basically how to handle services architecture while planning your network. Then we'll be moving to the design considerations. Essentially, it means which platform should I choose, whether modular or fixed, what are the best practices for each and every aspect of designing your network, and we are finishing with the integrations. Today, our agenda is slightly different because we are talking about the basics, so this is an introductory session. We'll be focusing on the foundational elements of the series agenda. However, tomorrow we are running BRK ENS 2500, and as you can see, we'll be focusing on more advanced elements and topics. So we'll assume everything we cover today. Tomorrow we will be just like reminding or building upon the foundation that we are building today. By the way, who's joining us tomorrow during BRK ENS 2500? Oh, very few of you. Okay, so that means that this is a signal for me to make sure I'll repeat the foundation, because a completely new audience then. All right. So this is the complexity map of and a time map of this session today. We are starting with the fundamentals of fundamentals. We want to just repeat the information that some of you might have already known, but we want to start with what campus network actually is. And by the way, this is the best slide. The first slide is the best to highlight that we know that it's not maybe aesthetic to use a yellow highlight, which flashes your eyes, but it's actually intentional. Within this 2 series long presentation, we'll be making sure that whenever you see the yellow highlight, this is something that out of the entire slide you should focus on. And talking about the campus, we need to realize that the campus focuses around providing the access to the network to the users or the employees of a certain campus and their network devices. So we already know that our main objective is to make sure that we will secure our network from malicious players, but also will provide a seamless access to the network to those that need the access to be granted. And the campus equals to geography. Right here, we've got a picture of Cisco San Jose campus. Some of these buildings are no longer in use, but years ago it was a vibrant campus with many buildings and floors within the buildings connected. So campus doesn't only restrict your network to a single floor or building, but campus could be made of multiple buildings which are in close geographical location. And we have to, as we are planning our network design, we have to figure out what is the interconnection between these buildings, which building will break out to the when, or maybe which will be the connecting point to the ISP, or maybe each one of these will have a separate internet breakout. And that's what we're going to focus on today. Yep. So campus networks are fundamentally not data center networks. And the reason is because the user or endpoints which we are connecting or are traversing through a campus network and a data center network are structurally different. And you can execute very clean runs in a data center because you've got basically the top of the rack and the end of the row very close to each other. Unlike in the campus networks, situation get messy. And I always like to throw these pictures for laughs, but the reality is why do we change or modernize networks, whether it's a data center or a campus networks? Because behavior or requirements of the endpoints connected to this network change. Who is the user of the campus network? Mainly human beings, and our behavior changed over times. 15 years ago, when we were going into the corporate offices, we still had majority of people connecting to the RJ45, their laptops or the workstations. Right now, you don't even have an RJ45 socket in your laptop. You're expecting the corporate to provide the wireless access. And how the wireless access is granted to your network? Well, you have to actually run additional cables. If the network was there for like 15 or 17 years, you have to run additional cables, install the access point, and run it all the way back to the rack unit somewhere where the switch is to power it up. And that requires actually running additional cable Ethernet runs and messing with the existing network. While in the data center, you can just rip and replace and everything is still clean and organized. Here, obviously, the golden rule, like if it ain't broken, don't fix it. That's why we end up with cables hanging on top of each other. So once we have the campus, well, fundamental of what we are looking at off the table, let's talk quickly about the places in a network. And why do we mean by the places in a network? In a multi-layer campus architecture, we differentiate three logical layers, obviously access, distribution, and core. We can extend or add additional responsibilities to each of these layers, like we can make sure that our core, as I mentioned on this Cisco San Jose campus picture, you can decide whether your core device will be the last touch point before you break out to the internet. Then we refer to it as a core as an edge or a core interconnect. We can also extend access, providing more ports for users or endpoints. This is an extended access. We also are able to collapse layers, and while we are collapsing, we always preserve the logical functions. We just cram more functionalities on a single physical box. So we took the fundamentals of the way very quickly because we will spend more time on the section 3 through 5. So a couple of principles as we'll be progressing through, couple of principles that will help us to, or will guide us while designing and building or architecting campus network in a multi-layer architecture. First of all, what multi-layer is? Well, we briefly mentioned that we always want to keep 3 logical layers in place, and it's for a reason, because every single logical layer has its own requirements, or requirements towards the platform that we're going to use. And sometimes or often we are asked the question, well, why don't you advise using, for instance, Catalyst 9300 as a core device? And honestly, if 9300 scale and is powerful enough for your use case, feel free to do it. It all depends what kind of a network you're running, how many endpoints you're connecting, what kind of a port density you require, and what kind of a resiliency you require from your core box, and how much risk you can accept. That's why we always, by default, recommend if it's core, you tend to use Catalyst 9600 or maybe 9500. If it's an access, 93, maybe 92. And if it's a distribution, you usually end up with 95 or 9400 series switches. And whenever you decide to do the dual functionality or maybe triple functionality on a single box, remember, you've got to make sure that you check all the boxes because logical layers don't disappear. They just happen to be represented on a single physical device. So multi-layer architecture allows us to scale out very easily because we can very quickly grow. If our company is thriving, it's very easy for us to just span another pair of core boxes and attach another distribution block and so on and so forth without disrupting the services running on an existing part of your network. So you can quickly add another blocks of your network and the other users won't even notice the maintenance window if you do it, if you'll execute it properly. But more importantly, we are creating fault domains, which are very convenient for us to operate, troubleshoot, and isolate problems. Because the golden rule of troubleshooting is, if you know what's broken, you can actually fix that. It's an 80% of a success to know where the problem occurs. And hierarchical design helps us to tame things. If there's a layer 2 loop, then you know where to look for. You're not going to look for the core boxes to causing problems. So here's a quick summary. Why do we follow these golden principles of multi-layer campus architecture? Because we are able to create small fault domains. There's a clear demarcation between layer 2, layer 3. We're promoting load balancing and resiliency baked into this campus architecture. It's really easy to grow or scale out or scale in, and very easy to troubleshoot or identify what the problem is. So hopefully at the end of this 2 breakout long series, you will be equipped with knowledge to leverage these building blocks to create your first or 100th network. And you will be also even more equipped to spot up the problems or not to build such networks or such weird designs which are, well, we happen to come across in our everyday life. So right now we will go through 3 layers: access, distribution, and core. And that's going to be, we'll cover just the basic fundamental requirements from each of these access, distribution, and core layers. But we'll also cover the oversubscription ratios and what it means for you, your requirement, and what does it mean for you to build actually 3-layer network. So access, we're talking about the campus access or extended access part of this multi-layer campus. And the main purpose, as we've already agreed, is to connect users, grant the access to the network to the users and their equipment. And that means that we are dealing with predominantly layer 2. That means we will be dealing with VLANs, .1Q, trunks, AAA, and spanning tree protocol. We have to enable functions like features like port fast. We need to control the storm, so storm control is important for us. We'll apply some sort of quality of service. More importantly, what it means for your selection of a box is that the box that you will choose to be your access layer switch will have to support low layer or medium layer 2 scale, and following by the feature scale, which is medium, because not much depends on this layer if you keep it classic. Important aspect, especially moving towards wireless only or wireless majority of the wireless connectivity networks, is the oversubscription ratio. And what is oversubscription ratio? Is basically ratio between the bandwidth offered on the downlinks in the access, in this case, in the access layer, and how much simultaneously you're able to push to the upper layer, which in this case is distribution. So if we would run quick math, like you can see on the picture that we've got, it's a stack of switch. I just wanted to break it down so it's very easy to get the point. We've got 4 links, 10 gig each. So access uplink, we are able to push up to 40 gig simultaneously. While if we assume that we have 48 port switches, and some of these ports are multi-gig, and some of the rest is 1 gig, then we are ending up with offering a 624 gig of a bandwidth to the lower, to the access layer. Well, if we run a quick math, it's the oversubscription ratio of 15.6 to 1. And the question is like, would you run such network? Would you leave it as is, or would you upgrade it? Well, the soft recommendation, if you look at the Cisco.com and a CVD for the campus layer, for the campus validated design, Cisco validated design for the campus architecture, you'll find the number, you've got to stay below 20 to 1. And in fact, you could still build all right, but if it's a stadium, or just before this session, there was an interview with the Real Madrid head of IT, and if that would be a Santiago Bernabeu, you would be really in a big trouble leaving it as is, because when people are coming to the stadium, they're pulling out their phone, connecting to the wireless network, and 15.6 to 1 oversubscription ratio would cause thousands of people present on the stadium during the break simultaneously using the network to drop packets, or wouldn't be even able to share pictures or use a social media. So it all depends on your use case. And we know that many people don't like the answer, it depends, but it always depends on your requirements and the characteristics of your network. So moving to the distribution, and you've got you know the drill now. We'll be following the same logic as with the access. So distribution layer requirements are, or the purpose of the distribution layer is to fan out connectivity. In data center, distribution is referred to as an aggregation, but in the campus networks, it's a little bit more than just aggregating or consolidating uplinks from the access and fanning it out to the upper layers. Here you have to also make an educated decision where the packet goes, because in a classic multi-layer campus architecture, distribution layer is the place where you introduce layer 3. And as you can see on the picture here on the right, in the blue we've got the access layer running layer 2 all the way to the distribution, and from then on, this is the demarcation point between these two layers. This is where we introduce routing. That means that the box that we're going to choose for the distribution layer device has to not only understand layer 2 at scale, but also should speak routing protocol of some sort that we chose for our IGP. That means we have to deal not only with the layer 2 problems, but also layer 3 problems, or solve these problems efficiently. That means that we need a high layer 2, layer 3 bandwidth, and we need to support the features in both worlds. So, quick math, what are the oversubscription ratio, or what's the recommendation for the distribution to core? So you know the drill. Right now we're looking at the case, we're focusing on this layer distribution. Distribution uplinks can push up to 80 gig per second, while in fact we are offering up to 800 gigabits per second to our down layer, to the access layer. That puts us in an oversubscription ratio to 10:1. So if you're a stadium, again, the situation was already bad on the access, it's even worse in a distribution. So the soft recommendation by the books, it's like you always should stay below 4:1. Right now, in the AI era, I know that you're most likely full of the AI talks, but the important fact is we are core and distribution, and especially in the data center, the ratio between aggregation and upper layer or backbone is 1:1, because the AI models require low latency, almost lossless connectivity. That's why if there is some sort of compute at the edge present in your campus network, then you should make sure that you will drive the distribution to core oversubscription ratio to almost 1:1. And in this case, I would start with adding crosslinks just for the additional resiliency. Doubling the uplink speed would help for sure, just to putting you off this danger zone of a subscription and dropping packets. Otherwise, you have to deal with the quality of service. So first order of things, if you have a budget, add uplinks. If you don't have a budget, think about the quality of service and which packets should you prioritize over the others. Moving quickly to core layer, it's the top, the most important for some, because the main goal is just simple. We need to switch packets or route packets at a high speed. We need, it's a transport layer between our local network, sometimes between the different parts of our network, ISP. This is purely layer 3. And if you will come across a situation that there is a layer 2 protocol running on a core, just make sure that you will push it somewhere else. This is no place for the layer 2 to exist. If you need to connect layer 2 services, then you better create a separate distribution block to which you will connect layer 2 just to stay safe. This is where we'll deal mainly with the EGP protocols like BGP or IGP protocols like on OSPF to make sure that we've got routing and SVI availability within our network. This is where you'll introduce sophisticated quality of service, but you can always source the information about the network, your network through NetFlow, for instance, just to get full telemetry. And many people ask, like, do I need a core layer? My network is fairly small. It's not a big deal for me to just operate it as is. Well, and that's true. If you have two distribution blocks with a couple of switch access layer switches attached to it, you can fairly simply run your network. However, if you keep adding more and more blocks, meaning your company, your network grows, then every new distribution block means you're creating a mesh of connectivity, of IGPs. You've got to tune all the all the small things and create IGP neighborships. And every new block is 12 new links, which are costly, and 8 IGP neighbors, and so on and so forth. It grows exponentially. So it's just really hard to operate and even harder to troubleshoot. The simple solution to that would be just simply add a block of core layer devices. And every new block is the same number of the IGP neighbors, the same number of new links, and it's really easy to troubleshoot because you just created demarcation between each layer and you've got fault domains which are contained to each other. So it's especially important when we were talking about this core layer that also is the last touch point before you break out to the outer world, or if you have many distribution layers or even core layers that you have to aggregate. So then the importance of the selection of the device that you're gonna choose for the core, for the super core, grows, and you need to really looking at you've got to be looking at the collapsed cores and edge layers, high scale, the highest scale of layer 3. This is where you introduce VRF's functionality. You've got to look at the scale, how many VRFs you support, how many IPv4 or IPv6 prefixes can you accommodate in your routing table. So these are important aspects or characteristics that you should be looking through the datasheet, and you've got to account for it. And this is something that you're planning before purchasing the device, not after. Because then we are often ending up in a situation, well, can I exchange the device that I've just ordered for a bit more powerful? Well, it's difficult, but possible. So we cleared the principles, fundamentals. We're moving slowly towards the services part. Before moving into this part, well, if you saw maybe this presentation previously, we were going like feature by feature, and I thought like, why do we talk about the features rather than we should be focusing on the services or features that are enabling certain behaviors or helping us to avoid certain behaviors. And this is how we should be thinking about the network functionality or architecting our network. What do I want my network to do, or which problems to solve? And then I'll think, okay, this and that feature does the job. I don't have to look at any other. So you might be thinking like, okay, someone is asking you, why did the traffic stop flowing out of nowhere? And you're looking it up, well, someone says, it's slow, I'm complaining there are drops, it works just sometimes, you're checking your dashboard of any sort, and well, everything's up, everything's green, where's the problem? And I wanted to flash one thing. It's really important to know what kind of a media is connecting or interconnecting your users and the devices because if you know that the devices are connected mainly through the fiber optics, then you know that unidirectional link failures can occur. And even though everything appears to be okay, if you don't have the unidirectional link detection, which is a feature, UDLD turned on, you won't even know that there are TX, RX mismatches, and therefore some users may experience problems, slowness, drops, even though everything's green in your network. So UDLD as a legacy feature is still kicking and screaming because it's really worth turning on, especially on the fiber circuits. Additional problems appear when you're simplifying network, and we are strongly encouraging you to do so because Ether channel are helping us to aggregate physical links, increase bandwidth, and simplify the logical construct of the network. However, if a member of the Ether channel fails, you won't see it, but someone will say, well, you know what, network feels slow. That won't cause, in majority of cases, upper layer protocol IGP to reconverge because you still have some bandwidth, but it will feel slow. That's why we encourage leveraging Ether channels, but if you do so, make sure that you will inspect upon troubleshooting that not maybe one of or two members of the certain link failed, and Ether channel contains this failure, so helps us to still keep the routing up, but it may feel like it's a slowness in the network. So sometimes before jumping to troubleshooting layer 3, make sure that you will look at the lower layer 1, physical one, before trying to solve the problems that don't exist. So Ether channel, just a reiteration, the main goal is to increase bandwidth, provide the link level redundancy, just simplify your network. Then it doesn't require you to run such a high layer 2 scale on a device that is connected through a bundled link. Oh, and by the way, I see that you're taking pictures. This presentation is already available on the Cisco Live app. You can download the PDF, and there are many slides which I'm not presenting because of a time constraint, but there are many more slides available within a presentation deck. If you want to use it, feel free. So, why did network melt? Well, apparently nothing happened, but we needed additional port density. Someone brought the old switch from our lab, and everything died, right? So we already know what happened. Network layer 2 loop occurred. And why did it occur? Because the Ethernet packets don't have time to leave, meaning time to life. So cascade of events, replication of packets happened, and control plane basically got melted, overdrowned by the data plane. So network, in case of a layer 2 loops, network just doesn't degrade, it basically melts instantaneously. And you may think, okay, layer 2, we are living in 2026, we don't need to look at the layer 2, but unless your network looks like that, or unless you're running rooted access and you don't have to worry about spanning VLANs between different access layer devices, then you still need spanning tree protocol in any way, because it allows you to, it's basically a seatbelt for our network to control it or not to completely melt when the layer 2 loop happens, or prevent layer 2 from occurring in the first place. That's the reason you've got to use or leverage spanning tree toolkit. And I know it sounds like an obsolete legacy. Now the management platform does it for you. Yes, but you've got to understand what you're using, what you're deploying, what the machine is deploying, so you can efficiently troubleshoot. So make sure that you as an architect will, if you're using spanning tree protocol and you're spanning layer 2 domain across different access layer switches, then make sure that you are in control of a spanning tree protocol. If you are using spanning tree protocol at scale, use PVST or Rapid PVST Plus, and PVST stands for Per VLAN Spanning Tree Protocol. MST is the multi-spanning tree protocol, so if you're bundling many or you want to create a spanning tree instance for multiple VLANs at a time, you can do so. Basically, learn how to use spanning tree protocol. There's no possible way that we'll learn that during this session today because it takes some time, but I'm just flashing the importance of not forgetting about the basic protocols, which are the foundation of every network build. And now, why did the network overreact to a small failure? Well, failures more big can expose bad design. So let's say that a single device failed for whatever reason. Then users across the building or in completely different distribution block felt it. Routing churn spikes, everything reconverges, takes minutes, not seconds. And well, although the failure was local, the reaction was sort of global. Too many devices reacted to the change. Why would that be? Well, there could be multiple problems, but first of all is like incorrect implementation of the first hop redundancy protocol, or maybe not using it properly. So always, even though it requires you to have one of the upstream devices to be active, the other to be standby, and inefficient use of a uplink bandwidth, but you've got to still remember about using first hop redundancy protocol if you don't have more sophisticated routing protocol between the access, like from the distribution to the core, because it allows you to reconverge quickly. The standby router will take up quickly, and you will be able to switch packets without black holing traffic. Then, always, if you are able to, use rooted interfaces, because in the case of a device or link failure, these reconverge and inform, or the routing information is propagated much quicker than over the layer 2 interfaces. So it's related to an auto-state service, because if there is an SVI available and apparently the link goes down, the auto-state service has to cycle through every port of the switch in search for the reachability to the SVI, and then it takes some time, and only after that the SVI is declared down and the routing update propagates. So make sure that you're using rooted interfaces when possible. Bidirectional failure detection is a perfect mechanism for you to detect failed link or device multi-hop or point-to-point, and it's extremely useful, especially when you're using the protocols like OSPF or BGP, because the timers are much faster on a BFD than they are by default in a popular IGP or EGP protocols. So make sure that you will use it, because it allows you to inform an upper layer protocol instantaneously when the failure happens, and you're able to reconverge quickly, and your users at the end of the access won't feel the change. So a bunch of summary takeaways. How should you plan your services? So always think about summarizing routes on a distribution. When you're bundling bundle links, make sure that you leverage EMCP, equal cost multipath. When you're building routing interconnectivity, make sure that you are building triangles, so there's no routing churn and devices are always connected despite what's going to happen to a link, to an individual device, or bunch of links. Terminate layer 2 at the distribution. Don't build huge or tremendous layer 2 domains. Use first hop redundancy protocol and summarize routes at the distribution. This way you will lower the scale requirements from distribution and following that to core. And we managed to get quite smoothly to the platform and then followed by the best practices section. And the platform and best practices are by far the biggest and most important parts of this presentation. So we'll go through the chassis considerations, and what do we mean by chassis? We'll focus on okay, so we discussed already that what are the requirements of the access, distribution, core layers, which services should I be running, what should I be having in the back of my head while thinking about the services. So what does it mean for me from the device selection? And on top of that, we've got fixed, we've got modular chassis. What do I do with that? How fast ports, how many of ports of a certain speed should I have in my network? Which features are impacting my scale and my selection of the hardware components of each platform? And that's what we're going to discuss right now. So, or I assume that you're pretty familiar with the Catalyst 9000 family of switches, and it's been with us for quite a while, and we keep extending that family with new additions. So earlier in 2025, we announced Catalyst 9350 and Catalyst 9610 switches, which are two additions on the spectrum of Catalyst 9K family, because 9350 is an addition to an access layer device, and 9610 is on a spectrum of usually this is a platform that you would aim for to be placed in a core, and especially at the scale, because it's a 10 rack unit chassis, so you have a place for 2 supervisors, followed by the 8 line cards, and those are of a high speed, high density line cards for your use. Nevertheless, classic Cat9K family still exists and is still supported and is going nowhere. So you've got a choice between high density, low density. You've got different form factors at your choice. You've got a modular and fixed choices for both core and access layer. And someone may ask why. And it's a great question, because it all boils down to a hardware that is soldered on the motherboard, right? CPU, ASIC, and PHYs. So CPU is responsible for running an operating system, for supporting certain features, while ASIC, this is the muscle, the heart of a switch, because it allows it's programmed by the software, and it's responsible for layer 2 and layer 3 scale. PHYs, they're transforming the electrical and optical signals on top of that. So the choice that you had, that we saw on the previous slide, I'll try to just revert it. It all depends how quick the CPU is, how big the ASIC is, what type of the ASIC is, what are the PHYs used on the motherboard. Meaning, it all boils down to how much speed you want, at what density, and what kind of features you want to run. Because some devices that you saw in the previous slide are not able to run certain features because of the limitations that we have from the CPU and ASIC perspective. And if you want to learn more, there is a great session, BRK ARC 2092, which I highly recommend you. I think it happened already or will happen tomorrow. So it's a great session that shows you the differences, slight differences in architecture, of different ASICs and how they handle different features and why they support them or not, and what are newest advancements when it comes to the ASIC architecture. So this is it's for the geeks, but this is where you will get most of the context why things are created or operating in a certain way. So now, big dispute is like, okay, I want to only have devices in my network which are like pizza box, right? I'm going to insert it, something happens, I'm ripping, replacing. I don't want to deal with the complexity of modular chassis, which is fair. However, I believe that in a perfect world or like very resilient architecture uses the best or the advantages of both. So you want to be able, or you want to use modular chassis where it has its place, and you want to make sure that you will leverage fixed box architecture. If you want to be, on the less complex side, easy touch, sure, go with the fixed boxes. That's the reason why we have platforms which support a core or distribution functionalities, both fixed and modular. But the oversimplification can become a burden. Let's imagine, look at this left-hand side picture. If you keep connecting or spanning a core layer to core layer and device using the fixed box device, you are ending up creating a full mesh network, while it could be replaced with a modular architecture just like that on the right-hand side. What happens if for this device, for this site, you've got 48 ports? What happens if you need 49th port? Where you either put one more box or you stack it with another. Then you've got to accept the trade-offs that you have with the resiliency and redundancy in this scenario. So don't be afraid, or maybe don't be biased to a modular buildup, because there is a mathematics that shows if you're crossing a couple of thousand ports of the same access layer, then you're better off, and it's cheaper for you to operate and run modular based access layer rather than fixed based. And there are two sessions, BRK ARC 2098 and 2099, which are going into details. So they are the deep dives into each access and distribution, as well as access and core and distribution platforms that we currently have, and the newest advancements along with the iOS XE advancement and feature supports. Okay, still with me? So cable considerations. Why is it important? And it's a busy slide, but the main takeaway is, in some cases, if the quality of an old cable, like Cat5e cable, is good, and the run is not too long, you can still achieve quite great speeds with that. And it's especially important when the wireless team, especially in the big organizations, the wireless team is running independent from maybe switching team. And that means that the wireless team is planning their refreshes independently from the switching team. And they may require you, by the way, we're installing Wi-Fi 6E or 7 next week. I hope that you're ready. Well, not really. My cables are old and my switches are slow, and I'm not ready to, basically the access layer will be bottlenecking everything that the Wi-Fi 6E or 7 bring into the table. So just keep in mind that sometimes the quality of a cable can help you with that. If the run is not too long, you can achieve great speeds, but more often than not, you're actually forced to rip and replace not only the switch, but also the infrastructure behind it. Important thing to keep in mind, the SFP stands for small form factor pluggable, and QSFP, quad small form factor pluggable. And that already indicates that QSFP pushes more bandwidth through each and every fiber optic cable, while the SFP is usually where you will connect access to the distribution with an SFP. And there are different speeds, different wavelengths. Single mode fiber allows you to transport more bandwidth for the longer distances, while multi-mode allows you to pack multi-thread, multi-optic into the multiple signals into one fiber optic, but then it travels on a shorter distance. So again, to the Wi-Fi 7 example, why I said that you might be bottlenecking the capabilities or the new achievements of the Wi-Fi infrastructure, well, because it all boils down to how many multi-gig ports you have. To support Wi-Fi 7, not only you need multi-gig ports, but you need 2 of them to fully use the capability of access point 9178 access point. So it operates on dual ports, providing you the redundancy, but it takes now, instead of 1 access layer port, your access point is utilizing 2 ports. Not only that, to fully leverage the capability of Wi-Fi 7 on its full scale, you need at least 57 watts per port across these 2 ports. So what does it mean to my choice of the access layer device? Well, I have to support UPoE, plus I have to have redundant power source units powering up my device. I need to have multi-gigabit available across all of the ports. And that actually limits the choice that you have from the fixed access layer devices. And then let's say that there will be Wi-Fi 7, maybe Wi-Fi 8, maybe 9 in the future, right? Then it means like, okay, I might be forced by the wireless team and a growing demand of the wireless-only endpoints in my network to be ripping and replace my fixed box, my access layer box, more often than a life cycle is, just to keep up with the demand. Then what's simpler? Ripping the entire device or swapping the line card of the modular box? It's the latter, right? It's just easier to unplug devices. Your control plane stays intact, and you're just inserting the line card, which is more capable, and you're replugging or reconnecting the access points, powering them up, and therefore offering more scalable and longer lifetime of the entire chassis. When we're talking about the ripping and replacing, often it's not possible, or it's actually the cost of the infrastructure change is greater than the devices upgrade. That's why there is the EcoFlex IT. They created the white paper, which I like the idea of like thinking out of the box. Why should I replace all cables where I can actually push access layer closer to where the users and the endpoints are? And this is a very valid design, especially when your office, your network is heavily dependent on the access, OT devices, IoT devices, maybe access points, and this building's been there for quite a while. Then you're basically investing only in refreshing the fiber runs towards the devices which are the access layer, and you've got just like last mile run for the replacement or refresh. That allows you to put the devices closer to when the end user is, under the floor, over the ceiling, behind the wall, and you can leverage this simplification. So if you didn't know about it, or it's quite logical if you think about it, but the application of the fabric to the active consolidation point idea is very interesting. And it allows you to achieve a lot and save a lot of money, a lot of OPEX, or just a hurdle of replacing old cabling around the entire office. And there is a session that was delivered 2 Cisco Lives ago by Jérôme Durand, my friend. I strongly recommend it. He's going over the use case that he had within his theater in France. One of the customers actually did that, and they were very happy with the results. So this is an alternative if your budget is limited, but you still want to refresh and meet the requirements of the modern standards of the network. Okay, one more try. Yeah, we changed. So this is a busy slide, and it's full of information, but I like the information in the top right corner the most, because I don't know how about you, but I always find it confusing to decode what actually 9500-48Y4C mean. And if you look at the top right corner, Y stands for 25 gig. So in fact, I already know that this box is 48 ports of 25 gig. And what does 4C mean? Well, I have to switch the slide because this is a higher speed. C stands for 100 gigabit. So just something that I found interesting always when I was thinking about the code names of the line cards and the devices that we offer. It's basically the port density and speed is baked already in the code name of the device itself. But this is not the main talking point of these 2 slides. It's important to know that most of the transceivers, most of the optics are running in a dual rate speed. And there's not much of additional money you've got to pay to pay for the optic that will run at a 25 and 50 gig speed. So there's like on average 10 to 15% more expensive optic that runs at the 50 gig than the 25. What does it mean? Sometimes to be to buy yourself a peace of mind for longer, you have to pay a little more. But then, for instance, when you're refreshing the access layer, you can refresh already with the dual rate optics. So optics that are ready to be run, that are running on a 25 gig but are ready or capable of 50 gig speed running. And then next year or in 2 years, if you will be refreshing data distribution, you no longer have to look at the access layer uplinks because they are already capable. You just make sure that the distribution is refreshed with the dual rate optics too. And then you just upgraded your entire uplink access to the distribution to a 50 gig seamlessly in just 2 steps, planning ahead. Some optics that we offer are of a tri-speed, so they run in either 10 gig, 25, and 50. So you've got a variety of choice, and it's a little bit extra, not too much of an uplift from a price point perspective, 10 on average to 15% between a 25 and 50, and you can achieve, well, you can actually save money in the long run because you don't have to swap the optics twice. All right, now feature considerations. And there's no time to go through all the features that go into the access or usually are seen in access, distribution, and core layers for both IPv4 unicast and IPv6 unicast. But what I really wanted to flash is like every single feature in here consumes some sort of resources on your device. The CPU, the ASIC resources, or the scale, and FIS. So if you think about planning the layer 2, you need to think about the number of the endpoints you have. And again, going back to this, it's not a wireless session, but going back to the example of the Wi-Fi 7, it means that your company not only requires you to provide a high bandwidth, but also will expect many concurrent users connecting through every single access point, which impacts the number of MAC addresses that you've got to stuff on each and every access layer device. And every single access layer device actually has to register. Every MAC of the access layer device is registered also in the distribution, because this is where we only introduce routing protocols. That means that if you follow the logic of 1 to 5 MAC addresses, like 1,000 to 1,500 MAC addresses per access layer device, and you've got like 20 access layer devices connected to each and every distribution device block, then you end up with 20 to 30,000 MAC addresses scale requirement just for the distribution box. And then you scale it out to from the distribution to core, so on and so forth. So, and if you look through the data sheets on cisco.com, you'll find out that this is exactly matching the scale supported by standard distribution, standard core layer devices that we are suggesting you to use. Additionally, keep in mind, access to the distribution over subscription is 20 or should stay below 20 to 1. Again, multicast, IPv4, IPv6 multicast features, or this is a solution, this is the way that you treat packet, but also you've got to make sure that the scale of a device supported number of the multicast session is there if you're leveraging the multicast heavy applications. Again, I'm going to use the Real Madrid stadium example. Their stadium obviously runs or heavily relies on the multicast application because this is the stadium you want to distribute. You want to distribute packets or replicate packets simultaneously and lossless, right? So when we are thinking about the MAC addresses, think about the number of ARP requests they have. It's at least per one MAC address, it's one ARP every now and then whenever it connects. If we're thinking about the IPv6, that's neighbor discovery protocol. And you know the difference between the IPv4, like endpoint usually has one IPv4 address, but the IPv6 endpoints tend to have all the way like even 3 IPv6 addresses at the same time. Single MAC address has up to 3 or even more IPv6 addresses. That means 3 or more network discovery protocol, NDP, neighbor discovery protocol requests per IPv6 endpoint. And that, if you start going through the scale numbers, you will quickly find out that you really have to analyze what kind of a network, how many devices of which type, IPv6, IPv4, if you're using it or not, you've got to have in your network and plan which applications will be leveraging what kind of a protocol, and that actually translates to the box size and box type that you're installing as a distribution or a core layer. And additionally, at the very bottom, if you're planning this device to peer with the internet, then the internet MAC IP table is already nearly 1 million in entries. So if you're not filtering and you want to import entire internet address table, then you're looking at over 90,000 IPv4 addresses. And then we're coming to the topic of equality of service. The golden rule is like you cannot push more through, like you cannot push bigger pipe through a smaller pipe. So it's as simple as that. But if you have to decide what you're going to prioritize. And the most important part of this slide is, remember, depending on the hardware type you've got or ASIC that you have, there is a different way of treating or queuing and prioritizing. So Silicon One does it in a different way than UADP 2 or 3.0. And UADP 2.0 or 3.0, this is the ASIC usually used, used in Catalyst 92, 9300s, while the Silicon One is the one that you will see in Catalyst 96, 9500X, and so on. So make sure that you just keep that in mind, because when oversubscription happens, this is where it's critical for you to prioritize the critical applications and signals and packets, and otherwise everything else that can wait will wait or will be dropped. So it's always the golden rule is like, if I have an oversubscription that is unbearable, maybe instead of looking for the quality of service, start thinking about upgrading the bandwidth or making sure the ratio is a little bit better. And there is a great deep dive session around the quality of service, BRK ENS 2096, delivered by the Ninad, who's the TME in Catalyst switching team. So he goes in the details of the platform characteristics and what it means for the application of quality of service to you. All right, and we've arrived to the best practices. So best practices is taking it all together and making sure that we understand how the decisions made about the access distribution core layer, the type of the platform we're going to use, they're all coming together, and also that we'll be able to leverage the best practices of designing a highly available network. So high availability, it seems like a lot, but it's going to make sense very quickly. For those that already know it, it's going to just make sense, or will reinforce the information that you already possess. But there are 3 different levels or 3 different aspects of achieving resiliency in the network. It's the architecture resiliency, operating system resiliency, and platform resiliency. And for the platform, it's simple. There are different capabilities that are supported by the modular chassis. For instance, you can have 2 supervisors, 2 control planes running at the same time. Therefore, if one fails, you always have second. But for the fixed also, you can run a stack where you have a hot standby control plane. So if one member or active member of the stack fails, you always have a standby control plane waiting to pick up the orders. So how does it happen? How does switch over between an active and standby in a modular chassis or a stack happens? We are leveraging the same subset of services, which is a stateful switchover that synchronizes all the active processes state as well as the running config between 2 members of within a modular chassis or stack or stackwise virtual. And we've got non-stop forwarding. And non-stop forwarding allows us to gracefully restart routing processes. So the hot standby knows, is aware of the neighbors, routing neighbors, and is able, upon a failure of the active, is able to pick up and start switching packets very quickly to known neighbors. The same happens with the stack of the switches. So it's very basic to what it does, but it's essential for all the other features that we'll be discussing afterwards. So SSO and NSF are the baseline of the hardware resiliency. We can leverage stacking. So stacking, you can stack right now, and that's about to be changed. So I strongly recommend tuning into a 9350 dedicated session. I'll show you the code, but right now we've got 8-member stack maximum, so you can bundle 8 fixed switches together to create a stack. That doesn't mean that you'll have 8 control planes running at the same time. That would be crazy, no simplification. We have 1 control plane, but every single switch switch data plane takes part in a switching packet. So you're basically making sure that you only have one control plane device. So you're controlling one device, configuring it from through one IP address. You're managing this device through one IP address. However, you've got 8 switching packets, and you can achieve up to 1 terabit of a total throughput, as you can see at the very bottom. And this is, I'm going to just say that this is the stack of 48-port 9300Xs bundled together, only achievable. 1 terabit is through 9300X. And again, the switch between active and standby happens based on the non-stop forwarding and stateful switchover. So this is the session I strongly recommend tuning in. I think it's running parallel to this one, but it will be shortly available on a VOD, on a Cisco Live VOD. This is smart switches deep dive, but also it goes over the new advancements or new features that are available in iOS XE based on 9350 platform. Basically, you are able to stack devices together not only through the back ports, but also through front ports. And Sean Wargo goes into details how it works, why would you want to do it, and what kind of a new architecture challenges we can solve with that improvements. So here, just a couple of clarification points. What can you stack with what, and what can't you stack with what? So within a 9300 family, you can mix models, or you can have only 9300X stack of 8 switches. You can mix that with 9300. However, if it comes to 9300B, these switches only stack with each other. The same goes with 9300L, and the same logic is reapplied to 9200. So you cannot mix a stack of 9200 with 9300, but you can mix some of the devices within 9300X and 93 together, B excluded and L excluded. It might be confusing, but you can always come back to this slide, and it makes sense. So whenever you're thinking about expanding number of ports, make sure that you will look what kind of a switch is already running in your network before you will buy another one to stack it with the existing infrastructure. And stackwise to its rule, its main goal is to expand number of ports and simplify network operation. So it's easier to troubleshoot, it's easier just to condense. You've got one control point of your network while having hundreds of ports available through just a single control point. Pairing it up with Ether channel allows you to achieve great resiliency and simplification of the network even before introducing any complex routing protocols in the upper layers. So we refer to it as a multi-chassis Ether channel because not only you're bundling the switch in a stack together, not only you're leveraging Ether channel, but every uplink comes from different stack member. So not only you're resilient for a single link failure, you're resilient when it comes to the single switch in a stack failure because your control plane will switch over to different device and you still have an active uplink paths to pick up whenever the failure happens. So it's like multi-layers of resiliency that are baked into simple functions, simple tools like Ether channel, stacking, and stateful switchover. So how it looks, if we'll break it down, traditionally leveraging just first hop redundancy protocol, we know it, we are blocking one of the uplinks, so we are inefficiently using very expensive uplinks. But if we would pack it together, so we are bundling links together in an Ether channel, additionally we're creating stackwise virtual pair. Then, from a logical perspective, spanning tree is not blocking anything because we are forwarding through both links up. We have one device, one control plane device from the logical perspective, but in a data plane, from a data plane perspective, both of these expensive devices are busy switching packets. So we're not losing any bandwidth with the high availability achieved by the stackwise virtual. And we can have different applications of high availability achieved through like first hop redundancy protocol we already covered. There is something which is called ESI MLAC, which is Ethernet Segment Identifier Multi-Chassis aggregation, multi-chassis link aggregation, right? So I like to decode the names. That explains already a lot when it comes to what actually is behind this acronym. So ESIM-LAC is popular because the EVPN protocol takes care of synchronizing routing tables and routing state between two independent control planes, while both of these devices, through ESI, so Ether Channel Segment Identifier, they are aware to which device they are connected downstream at the same time. So they are able to synchronize the state of their routing, and they are able to participate in a data plane switching. So it's a very efficient way, because you can have, well, technically you can have two different devices running different code, and you're still able to achieve through ESI-MLAC very efficient redundancy on a data and control plane level. So that means that you can upgrade this one independently from that one, and you can still actively switch packets, and nothing is disrupted between these two. However, Stackwise Virtual is still superior because you only have one control plane device to control. It's a single touch point, and there's so much more resiliency baked into iOS XE that are making your life simpler, and also the upgrade of the operating system simpler, which we'll get into on the next slide, that it's still a valid use case to run Stackwise Virtual, because it's a proven, it allows you to jump from one version of the OS to the other seamlessly with a minimal downtime, and you've got very simplified way of operating your network. So when I mentioned that the Stackwise Virtual allows you to seamlessly upgrade your software while still switching packets, I meant in-service software upgrade functionality. In-service software upgrade feature allows you to jump from within a train of iOS XE, meaning you can jump between different versions of iOS XE 17.1 and so on. You cannot jump between major trains, so you cannot jump from iOS XE 17.1 to 26.1, for instance. For that, you will require longer downtime, and it's related to what we call the microcode upgrade that happens between major releases, and that requires a longer planned downtime. But how ISSU works, you're basically attempting, you've got an active and standby control plane device. Then first you attempt to upgrade the standby. If that's successful, stateful switchover and non-stop forwarding help you to switch active with the standby. You do the same for the previous active, and if that's successful, basically the ISSU is finalized, it's finished, and changes commit. At the end of this process, which takes takes no time, you're only switching active with the standby control planes. We didn't leave single, like a fixed chassis alone, because you also have something that is called extended fast software upgrade on a standalone, like 9300L or 9300X. Starting with the 17.15.2 iOS XE, you're able to leverage extended fast software upgrade, which takes down the entire downtime below 5 seconds. But it has some caveats. Please read through the data sheet and the details of this feature, because it all depends which features you've got turned on a device in iOS XE, and that determines how quickly you can actually perform XFSU. But in some cases, in majority of cases, it's below 5 seconds. So this is the command that you are triggering XFSU. The control plane upgrades from version 1 to version 2. Data plane is still running, and once the control plane upgrades is done, which usually takes most of the time, most of the downtime is the control plane upgrade, then we are basically loading the cache to the ARM processor of the data plane. Data plane code is being upgraded, which usually takes below 5 seconds, and we are able to pick up where we left off. Still with me? Yeah, good. We've got a couple of slides left, but these are really important functionalities which, well, if you put it all together, you'll see that, buying Catalyst 9300 already buys you most of these functionalities, but understanding how the functionalities work or what can you enable or turn off really helps you design your network with a thought behind it, right? So power high availability is important. We talked about it. You're powering more, and especially if we're talking about the Wi-Fi 7 or Wi-Fi 6E, these are power hungry access points. So you might want to invest in a stack power or power redundancy at the same time. So not only we are providing the redundancy on a data or packet switching level, we are also providing redundancy on a power over Ethernet level. So if we're looking at the stack of 8 switches, within a stack of 8 switches, you can have 2 rings of power, basically. So 4 switches create a ring of power, and then the next 4 switches within a stack of 8 switches create a second ring of power. And within this ring of power, you've got the shared pool of power, and this pool of power can be used simultaneously by all 4 members of it. That allows us to achieve further, like deep level of redundancy, because every single switch only drains as much as it needs at minimum, and the remaining power surplus is just available to the other members. So should one PSU fail, you can still, as long as you've got a budget, you can still function, and the connected devices won't even feel it. And there is a very good session, and it's running this week also, BRKNS 2095. I strongly recommend you joining this one because it will go over all the high availability features that we have across Catalyst 9000 family. It's a great starting point for your journey with the HA in general. Okay, and we covered the high availability, so we know what we have from the software, from the platform, from the power perspective. Now we want to secure ourselves from the external dangers and also internal dangers. And I believe that there is the saying that the chain is as strong as the weakest link, and the same goes with the network, because your network is as strong as its weakest element, which is the basic switch on the axis. And we start with the story of a fish tank. I don't know if you've heard of it, but there is a story of, well, basically not necessarily a fish tank, but a smart thermometer, which was placed in one of the casinos in Las Vegas. And the hacker, he noticed that this is like the smart endpoint exposed. And long story short, this person managed to export very valuable data of the data center, from the data center of the casino to the external servers, and exploit the casino, highly valuable customer list. It cost the casino millions, but how it happened, it was because the IoT endpoint was not secured. That's the first thing, and the other thing, it allowed the connection remote. It allowed to establish remote connection to the data center part of the network of the casino. So we want to meet our requirements of a modern network where we are, meaning we want to invest in OT endpoints. We want to make our offices smart. We want to have smart thermometers, cameras, but we cannot forget about the segmentation of our network. So we'll get back to this story in a couple of minutes. But going back to this weakest link, every Cat9K device is equipped with a switch integrated security features. And it all boils down to the device tracking capabilities. So device tracking service makes sure that we are detecting neighbors and users and endpoints connected to the device. We are inspecting them, tracking its state. We're guarding and gleaning the address of a connected endpoints. And we are storing all of this information in binding table. And this is what we referred to as SISF infrastructure. And it's really important. Maybe it's like geeky information, but it's really relevant to the next part of what SISF is leveraged by. So if we'll go further, you'll see that we've got certain features and clients which are leveraging SISF stored information. And these features are already very familiar to you, or these services or protocols are very familiar to you, right? So layer 2 DHCP relay, or Cisco TrustSec, or EVPN, 802.1x. These are all the features which are pulling information which are gleaned by the SISF infrastructure, from the binding table, which associates MAC address with the port, with the IP address of a connected device. So this is your potentially weakest link, but if it's strong, and if you're sure that the service is running, or if you know what kind of services are running and how they work, you're sure that your network is resilient even from the malicious players or malicious endpoint, because we are building on a strong foundation. So how you can actually apply what we have, there are different ways to secure your connectivity. it's very popular right now to expect that the network will be able to have MACsec security of the link, and not only device to device, but more often we see that there is an expectation that the supplicant on a laptop of the employee connected to the network will also have a MACsec securing this link. We are supporting on the Cat9K, we're supporting layer 2 MACsec both on the link device to device and also endpoint to a device, endpoint to a switch. You are likely aware of the layer 3 encryption methods like the IPsec, and you can span an IPsec between different devices or between even the cloud, and you can establish from a Catalyst 9300X or 9400X, you can establish an IPsec connection, encrypted connection seamlessly, so you don't need a router to do that. And moreover, 9300X and 9400X are running, they have dedicated HiSec engines soldered on a motherboard. So you have dedicated engine which only job is to encrypt traffic on the fly. For 9300X is up to 100 gig per second. For the 9400X is up to 300 gig per second. So very powerful, very like huge bandwidth off the bat with the switching platform. So once we know that device itself is keeping a track of the endpoints and we are making sure that the connectivity is secure, and whenever this change happens, we are tracking that. Now we have to start thinking about like more macro level across our network. So thinking about how, what, who. So the answer to the question how is, how am I authenticating certain endpoint or user into the network? And there are different ways. Like you can authenticate through the web auth, you can leverage .1x, VPN, or MAC address bypass authentication. So you've got a variety of ways. But important thing is, despite what is the method of the authentication, you've got to make sure that you're collecting contextual data. So you know what's the ID of a device, when it connected, how it connected, what's the application that's connecting it through. So you are creating the identity map or profiling your endpoint and user. And it's really important to start thinking about collecting or profiling endpoints and users. ISE, Integrated Services Engine, helps with that because you can answer to these questions while authenticating, onboarding users into the network, and at the same time, you can leverage this information to your benefit. So how it works, like ISE is your AAA server, user is being authenticated, or endpoint is authenticated, ISE stores all the information about that user along with the contextual data. For instance, you can set what level of the data is being stored or leveraged, but you're even able to create policies based on the OS version of the laptop that is being run on a specific endpoint. So we've got something like an endpoint profile, and then further integration with the management platforms like Catalyst Center or Meraki dashboard allows you to collect the information from the connected devices, but also leverage that to authenticate users connecting into this device's network. So there are some certain unique functionalities, as you can see within a Catalyst Center. There are unique functionalities upon integration with the Meraki dashboard and ISE. However, the centerpiece doesn't change. The ISE is the common policy engine that allows you to globally control a policy, security policy for your campus network and beyond, adding you also the visibility. If we look at the relation between ISE and Catalyst Center, and we put the capabilities of Catalyst 9K devices on top of that, we can have a nice equation or nice like full picture of what we can achieve with this integration. So deep packet inspection looks into the header of the application packets, the packets which are being transmitted through the switch, and we can get an additional intel based on the behavior of the application or what application is. We can feed that information into endpoint analytics of Catalyst Center. Then endpoint analytics feature of a Catalyst Center also is being fed by the ISE profiling, that information gathered during the authentication and authorization into the network. And we have machine learning profiles which are crunching this data. That means that right now we have all information, contextual info about our endpoints, and Catalyst Center can leverage that. How can we leverage that? Because Catalyst Center can tell you how much of a trust will you give to a certain endpoint or user, depending on its behavior, depending on the rules that you're going to set up. So we'll assign a trust score to a device based on the deep packet inspection. So what kind of applications are being used by the user or endpoint, depending on the profiling. So what the endpoint is, what version of OS it's running. Maybe it's running the configuration that is no longer supported or advised by our security team. And also machine learning, like if the behavior changed suddenly, or maybe the user endpoint is trying to access the resources which is not supposed to access. This way, if the behavior changes, we can lower the trust score. And guess what? The trust score can be one of the elements of the authorization or policy authentication rules in ISC. So we can actually tell if the trust score of my endpoint is 7 to 10, then this is allowed user full access within the corporate network. However, if the trust score is below 5, then I want this user endpoint off my network. It's no longer trusted. And that could be various reasons, and you are in control of the reasons, you're in control of the policy, and the Catalyst Center with the endpoint analytics and the trust score, they are constantly tracking the trust score of a device. So it's not like once a day, it's instantaneous. So if you haven't heard of it, or if you didn't think of it, make sure that you play with that. Ask Cisco sales to show you how it works, because it's very powerful once properly deployed. And it allows you the end-to-end control over your network. So when we have a visibility, what do we do now? So we already said that if we have a proper AAA server that collects all the contextual information and profiles devices and endpoints, then how we can use it. Normally, we were destined to VLANs, dynamic VLANs, or we were forced to use access lists. But these are, I wouldn't call obsolete, but they're legacy ways of controlling the access or limiting the access and segmenting the network, and not necessarily scalable or very, very limited when it comes to flexibility. So how about we stop thinking about the user IP address as being associated with user profile or security profile of that endpoint or username? Well, ISC allows us to assign something called security group tag. So you no longer think about the security and profiling of a device based on its IP address, but based on its contextual data and profile. Basically, if the user if it's a corporate user based on a username or supplicant running on the device, then I'm going to assign SGT5. If it's a finance, I'm going to assign it an SGT8. And if it's a IoT device, I'm going to assign the SGT90. And then you can very quickly replace complex access lists, which are IP-based, to an object-based security group tags. And you can be very specific, because you can allow the communication between, for example, the auditors and the other SGT, and you can specify on which port the communication is allowed, or maybe that's going to just that's going to be unidirectional communication, not bidirectional. So you no longer are constrained to a segment of the network, because your SGT is carried over with you no matter which part of the network you're connecting through. So it's a dynamic assignment of your intent and adaptive policy that is based on an identity and trust score. Then we can take, assuming that we already have security group tags, then we can take to the next level. So Catalyst Center allows you to deploy an SD access, and the core elements from a security perspective of SD access are virtual networks, which are VNs or VRFs in the routing world, and a security group tags, which are SGTs. So virtual networks are allowing you to segment your network in bigger chunks. So let's say corporate users, campus users, and building systems. And I don't see a reason why building systems should be allowed to talk to corporate users if it's not a building manager, right? So we can, by default, the VN communication is not allowed. However, we can be even more specific by making sure that within a virtual network, we specify different security group tags. And we can specify, as we already saw in the previous picture, which security group tags can talk to each other. And it's very powerful, because you already remember that the IP address doesn't matter. It matters who you are on my network, what you do, and it matters how you behave. And then I can assign a security group tag based on that, and I can be very prescriptive what kind of connectivity you can run within my network or within my chunk of the network. So SGTs and virtual networks, macro and micro segmentation are really powerful tools. Once applied properly, they're helping you, they're not standing in your way, and you're simplifying many things from the security policy perspective. So if you still remember the fish tank story, or smart thermometer, proper visibility profiling would help greatly because we would very quickly observe abnormal behavior, so the trust score would be lowered. But if we would have, if the casino deployed a virtual networking or VRFs, there is a high chance that the smart IoT thermometer wouldn't be placed in the same part of the network, segment of the network as data center, or at least this, by default, this communication wouldn't be allowed. But if there would be even a slight chance that these happen to be in the same global routing table within a casino's network, the proper SGT assignment wouldn't even allow that communication to happen because there's no chance that someone designing a policy matrix would allow IoT devices to directly establish connectivity to data center servers. So if we'll take it even like one step back, on a global level, you are using likely multiple vendors which are helping you with the visibility tools or collecting the data from different parts of your network. And you can leverage Cisco extended detection and response solution that will crunch it all together and give you the actual visibility on the security, but also the state of your network from security perspective. So you can collect the intelligence across Cisco components, leverage the Talos, leverage the AWS flow logs, syslogs, net flows, and you can have it all represented in one dashboard, which collects telemetry from multiple sources, well, ISE including, and you have a full visibility across your network. Plus, obviously, you've got access to the tools which allow you to the further analytics of the behavior and mitigation of unwanted behaviors in your network from a security perspective. So the link to the demo is right there. It should be accessible from the PDF. And if you really want to learn about the end-to-end security, I strongly recommend BRK ENS 2602. And that takes us to the last part. So taking it all together, we've learned about the access distribution layers, different types of models, fixed modular chassis, and now what do we do with that? Maybe there are new and modern ways to deploy networks and operate networks, and this is where the virtual networking comes in handy. At some point we thought, like, what about not dealing with layer 2 entirely? How would the network work if we would push the layer 3 all the way to the access and we shouldn't be dealing with the STP at all? Great idea. It's called rooted access. And who's using rooted access? 1, 2, 3, 4, okay? 10 people out of, I'd say, 200. So that shows you why rooted access might be not the most popular solution. Why would that be? Because of a price. Sometimes when we're thinking about the rooted access, it's a great idea, but not everywhere you're allowed to do that because you need layer 2 adjacency between different access layer switches, but also that pushing requirements of the layer 3 on the access layer devices, which automatically is increasing likely the price of the license that you're looking at, or maybe the capability of the device itself. It cannot be only layer 2 anymore. But that's the reason why initially rooted access wasn't greatly adopted, but it's very handy to whoever, like if you're operating rooted access, you know that it's really handy, it's really easy to do that. So I strongly recommend exploring the idea of rooted access, or maybe going all the way to a virtual networking or overlays like the EVPN or Lisp SD access-based fabrics, which are basically rooted access with additional features like macro and micro segmentation. So the main difference, as we already, main purpose is to get rid of the layer 2 from your network and make sure that this point of change between the layer 2 and layer 3 is already introduced into access. I'm gonna move forward. So this way, we are not dealing with the layer 2 related problems, but we are actually creating a smooth transition already at the access layer and we're participating with routing already from the access. So building on the rooted access, we thought like, how about we will just don't care about the physical buildup of the network and we'll create a tunneling however we want. That's called overlay network. And as the access or EVPN, BGP EVPN, VXLAN is used to create the tunnels between specific parts of the IP networks. So under the physical connection could be whatever you want, as long as you have an IP connectivity and you've got maximum transmit unit. Well, usually it's a jumbo frames that you want to enable, and then you can run encapsulation on top of that. That allows you to extrapolate the physical layer, physical connectivity from a logical construct overlay. And you can use different mechanisms to achieve that. This way, you're able to have different protocols to take over the control plane connectivity, like the MPLS, like EVPN or Lisp. And at some point, well, the MPLS is an overlay. It's an overlay solution. So it's a virtual networking already, and it's been there for years. It's very well known, but it was limited to only macro segmentation, while EVPN in its initial form also didn't have a micro segmentation baked into the solution. That's why Lisp was introduced and was widely used and is still widely used by the SD access solution because it was scalable very well. It was scaling very well, and we've been leveraging VXLAN for the encapsulation and creating tunnels in the overlay network. Additionally, we were able to use the element of VXLAN GPO, which is group policy object, which allowed you to carry information about the tags of virtual network of attack along with a security group tag. This way, we could achieve within an SD access based on Lisp and VXLAN GPO, we could carry information about your macro and micro segmentation, and we can enforce that across extrapolated build that was created on top of different physical buildup of your network. So underlay is irrelevant as long as you've got an IP connectivity between different elements, because overlay is what it matters, and you're just looking at the logical construct. So if you want to learn more about the options which are available to you, different overlay, different virtual networking solutions, I strongly recommend tuning into the session BRK ENS 2501, which describes in details what are your options with iOS 6e and Cat9K, and you're able to really deep dive into all the possibilities that are at your fingertips. Also, there is the session 2502, which deep dive into this best practices of the SD access, particularly based on the Lisp. So, we are almost to the end. We managed to go through the foundational services, principles of multi-layer campus, along with how do we look at the services, what should we enable by default, the different platforms and best practices. So right now, it's just as a summary, remember that you always have 3 logical layers. If you are pushing the capabilities on the one physical box, it doesn't mean that you're removing the necessity to support all the logical functions. Remember to build or to leverage these building blocks. Don't build a mess, or if you've come across the mess, make sure that we are hopeful that you'll be able to equipped with the knowledge to fix these. That was the agenda of what we covered today. Remember, you are always able to leverage to leverage the new advancements when it comes to, especially to the fiber links, because you'll be surprised how quickly we are advancing in the fiber optics technology. So you can actually leverage 10 or 15-year-old fiber and still be able to push more and more bandwidth through that. Remember to leverage Ether channel stacking, the baked in the platform redundancy and high availability. Think about the next level of security, leveraging virtual networks, VRFs, and secure group tags, because it will really make your life easier and your network much safer. There are a bunch of materials related to Cisco validated designs on which this presentation was based off, so I strongly recommend you to check it out. Continue your education. There are in a Cisco Live app, you'll find many learning maps that you can follow. This was one of the 2 long breakout session series. I strongly invite you, if you haven't done so, maybe explore the idea of joining us tomorrow during BRK ENS 2500. And having said that, I would like to thank you very much for the attention. And have a great afternoon and the rest of the week.